Welcome to Chips and Salsa, where we talk security at Intel. I'm Jerry Bryant, and today I'm excited to have Vivek Tiwari join me to talk about negative space testing, which is something we've featured in our 2026 Intel Platform Security Report. Vivek is a vice president in the Intel Product Assurance and Security Group, and he's responsible for things like critical security issues that affect our products. He also leads the Intel Platform Update and long-term support programs. And last but not least, he works to improve the security of our future products. Vivek, welcome.
Thanks, Jerry. Really excited to be here. And our conversation today is really related to that part of my role where we drive security hardening, security learnings upstream into our products. So excited to talk about that.
So Vivek, when we talk about negative space, what is it that we mean really, and why should we care? Why should a customer care?
Sure, right. I mean, it sounds like negative space. Why should we care, right? And if you intuitively think about it, you're designing a system, a function block, an IP block, and you say, well, I'm going to receive some inputs, and I'm operating under certain conditions, and I need this system to do something. So press button A, something happens, right? That is positive space. That's the intuitive sort of understanding of what we would call a functionality of a product. That's positive space. But what happens if you get an input that wasn't something that you expected, or the conditions, operating conditions of the part are different from what you were expecting? That's negative space. Let's try to go a little bit deeper in this, right? And we'll think of a 4-quadrant model. And I don't know if you read any MBA books or anything on management and organizational learnings, you will always see these 4-quadrant graphs, because I think 4-quadrant graphs are intuitive to understand. So our team came up with this simple explanation of negative space in a 4-quadrant graph. So try to visualize this, and then I'll give you a simple example, which will hopefully make it more understandable. Vertical line, think of it as a positive space above it, negative space below. Positive space means valid inputs, things that you expect. Below the line, negative space, negative inputs, things you don't expect. And then divide this vertically into 2 halves. So you can say, on my left is my specified behavior, and on the right is unspecified behavior, right? So, okay, so 4 quadrants. So now let's think about the positive space. I get a valid input, and I specify what needs to happen, right? So this is exactly what the system is built for. This is the positive space that you've built for. All fine there. And you're going to validate that. But what happens if you get a valid input, but you are in the unspecified quadrant, right? That is kind of an odd situation. It sounds like your system is not designed to handle something that can occur. There's clearly a bug. So that's an architecture bug, and you want to look for those as part of your validation. Now think of the negative space below the line. Now if you get an invalid input, what's supposed to happen, right? You would intuitively say that I don't want my system to go haywire the moment it gets a negative input. I want it to handle that gracefully. So in architectural terms, we often call it error handling. So have you created or architected error handling for these invalid situations? So that is still part of your design specification. But you can have situations where you didn't think about an input condition that could occur, or a situation that occurs and you didn't build any error handling for it, or you didn't build any graceful handling for it. That is potentially a security vulnerability. So think of this as our 4 quadrants, right? Let's think of a simple example. Now, I often find it very interesting that I find the Mission Impossible movies to be great examples for security learnings. Ethan Hunt, Tom Cruise as Ethan Hunt, right? So if you are architecting a high security building, you are thinking, as an architect, you're thinking about the rooms, the hallways, your lobby, your elevators, right? And you want to make sure that they are super secure, they have access control. But what about all that other negative space, the service elevator, your service shafts, the air ducts, the service closets, right? The hackers are not going to live in the positive space. They're going to live in this negative space. Ethan Hunt is going to crawl through your air duct. He's not necessarily coming through the front door, right? So you can think of this as another concept of negative space in the bigger picture.
Yeah, so I think you did a pretty good job of explaining what negative space is in general. But let's go a little bit deeper, and why is it such an important focus now from a hardware perspective?
So let's go back to an architect. Now let's say you're an architect of a digital system, right? And let's say it's an IP block that communicates with other IP blocks over a bus. And it's a message-based bus, and you're sending packets. And a packet has a header that describes the functionality of the packet. It probably assigns a security attribute in the packet, right? If you're an architect, you say, I'm inside my chip somewhere. I'm assuming that I will only get valid packets. Why should I put in the effort to think about what will happen if I get an invalid packet? I'm inside a hardware block. I won't see this. Or you can have a situation where somebody says, yeah, it's an illegal opcode, or it's an illegal transaction width. But my operating system, it's a well-behaved operating system, it will never create a situation like this, so I don't need to worry about it. Well, guess what? Hackers are not well-behaved. Right? This is exactly where they'll go for, right? Those are the negative the crawl spaces and the service elevators that they're going to look for. So in the context of hardware, you have to think about these edge cases or these corner cases, right? The scenarios where you have unexpected inputs, unexpected configurations. So these are very relevant for hardware design. And since hardware is your root of trust, is the base on which all your security layers are built, you want this to be secure. So you need to think about negative space when you're designing hardware, because it gives you that extra layer of protection. And some people say, well, how isn't that basically error handling? And sure, it is error handling, but error handling people often think of in the context of functionality of the feature. Right, that if I get a condition that could be an error, how do I build it into my functionality? I think in this context, we are just expanding the definition to things which may not be obviously relevant for functionality, but they become relevant for security when you think like a hacker.
Awesome. So sounds like negative space in hardware could be a very enormous topic. There are a lot of ways things could potentially go wrong. How do you go about exploring that space at scale and actually make it manageable?
So it seems like it could be a large space, right? Like if I'm building my positive space, everything around its negative space is huge. It can actually be compact. And especially when we think in terms of hardware, right, and the scenarios under which hardware blocks operate, you can narrow it down even further. So for example, you can say, what I really care about from a security standpoint is an interface that is somehow interacting with the external world. Now, it can be interacting in a designed way through a programmable interface, or it's exposed to the external world. Let's say it's a bus that's running on your system on a chip, and the bus is exposed on the package. So in a way, it's exposed, right? So it's not meant to talk to the external world, but it's exposed to a hacker, who can do a physical attack on the bus. So we can worry about those situations, right? We can prioritize and say, let's not worry about everything. It's those kind of constraints or IP blocks are the ones we worry about, right? You can similarly say that, I have a situation where I know by design that my transmitter and my receiver, they're both embedded inside hardware, and my transmitter only talks to this receiver. So can this receiver then say, since I trust the transmitter, I don't need to look for malformed packets or illegal opcodes, because I will never get them from my transmitter. And if you can then, by design, you can verify that the transmitter will never do it, whether it's through verification, you can even do formal validation, and then you can say, I know in this case this will never happen, it's provable, so I don't need to worry about it. So you can prune your entire what might look like a large negative space into things which are meaningful and relevant. So this is how we do it. There are tools that can help you in this. Formal verification, which I believe that you will be talking to Jason about this in more detail, right? Formal verification is a powerful tool here because it gives you a mathematical property, and it gives you access to a large set of tools and research that the community has, the EDA community has built over the years, where you can have mathematical proofs and compact representations and very efficient solvers. So they can navigate this negative space very efficiently. And in fact, negative space is one of the strongest proof cases for formal verification. So through targeted approaches and tools, you can navigate what might look like a fairly intractable problem.
So when a lot of vendors talk about rigorous validation of their products, perhaps mostly they're focusing on happy path behavior. How is Intel's approach different when it comes to negative space, and how do we engineer for those undefined conditions by design rather than, as an afterthought?
So I think the key phrase is right there, engineering, right? So I think we use the word testing, and we talked about negative space testing, right? But I think the better way to think about it is negative space engineering, thinking about this from the beginning as a holistic problem from the beginning to the end, right? So validation is a necessary step. It's a last line of defense. But it's better if you build this in from the beginning, and that's the approach that we take. So you think about your negative scenario right from the time when you are documenting your architecture specification, then when you are designing the block as a designer, and then finally when it goes to the validator for validation. Think about this from the beginning. That is the more holistic approach, and that is the approach that we take that I think allows us to do this in a scalable manner and in an efficient manner. So for example, let's go back to this idea that if I have to handle these error conditions, it takes more overhead. It's design overhead for me. I have to put in this extra gates for this. I have to think about the validation strategy. But if you do this upfront, you can actually do it more optimally, right? Versus having to add it later as an afterthought. Similarly, if you expect a validator to figure out all your negative cases and build tests for them and validate them, it's putting too much burden on that. And as an architect, you actually have the insight on what's positive, what's negative, and you might be able to provide insight to the validators to help validate that negative space. So I call all of this as negative space engineering, right? So it's a systematic approach all the way how to look for, how to document, how to design for, and then validate the negative space. And that's the approach that we take. How do we help our architects and designers to do this, right? We give them guidelines, we give them policies. We actually have threat models that they can use that will help them navigate this. And then we also give real examples, because sometimes an example of a specific scenario from an existing design is a powerful motivator to go do something about it. Right? So I think what makes our approach unique or powerful is this taking it as a holistic engineering approach versus just as a validation or testing approach.
So many customers are now treating silicon as part of their security architecture and not just an IT purchase, right? So when they evaluate suppliers, what questions should they be asking about negative space testing and security hardening in general?
Let me even go back further up, right? I think if you are in the position to make a purchase, right, or you're making your purchases for your company, of your business, you should really be asking about the overall security assurance processes, capabilities of the vendor, right? Do they have, starting from the top, do they have a secure design lifecycle? Because a secure design lifecycle ensures an end-to-end focus on security from the beginning to the end, right? What that means is, if you have a secure design lifecycle, you are thinking of security as integral to your product design, not an afterthought. Then let's just say your products are in service. You're running your fleet on them. Right? New security issue is discovered. Does your vendor have the ability to patch the system? Remember, we're talking about hardware, right? Are there features built in that allow survivability or resilience, patchability? Do they have the capability to be staying ahead of hackers in their own internal research to find issues first? It's all part of an overall security posture and the security assurance strengths of your vendor. And a systematic approach to negative space engineering represents a vendor that thinks about security from the start. Right? So that's what you're really looking for, right? Because you are going to be running a system for a long time. Your business is running on a system for a long time. Was it built to be hardened against new threat vectors that may emerge later? And when these new threats are found, is there a policy to help patch your system or update your system to account for that? Right? So I think it is really about all of that is what you should be looking at as a customer, right? And it's not just about the bright new shiny security feature. It's really about the base functionality and the security hygiene of the base functionality, and the ability of the vendor to support the product.
If I'm a customer running a large regulated environment, what do I actually gain from a platform that's been hardened through formal verification and negative space testing and other such programs?
Yeah, I mean, I think what you're really buying is peace of mind. And let's elaborate on that, right? So, security in general, right? It's a race between good actors and bad actors, right? Or it's a race between your product design and hackers. Right? So, between the time a product is conceived, it's architected, it gets to market, and then the long number of years that it could be in service, that can be a long period of time, at a time when there's so much attention on security from our bad actors, right? And especially on hardware security. So at the time you designed a feature or you designed a certain protection between, and the time that the product is being in its operable lifetime, a lot can happen. Hackers are getting smarter, new threat models can emerge, right? They're coming up with new tools, new techniques. They can start chaining attacks together. So what you are getting from negative space is sort of defense in depth against that. So think of it this way. If I just say that I'm operating at this lower level, the upper levels, the layers above me, are meant to protect, right? I don't need to worry about certain scenarios because there's a layer above me that will protect it. But what if that layer is breached? All of a sudden, your assumption on, well, I had negative space on my lower level, but it will never be exposed because I have this upper level that's protecting it, right? But let's say that got breached. Then all of a sudden, your negative space that you thought was not relevant is suddenly relevant because it can be breached, right? So this is what happens in, castle design, right? If you're a Lord of the Rings fan, Lord of the Rings, the two towers, the outer walls are breached by Saruman and his Urukai. They blow up the outer wall, but then you have the inner wall and you fight for the inner wall, right? So it's defense in depth. In hardware design, an example of this could be that you are talking to a firmware agent, and that you have an IP block talking to a firmware agent, and that firmware agent is trusted because only you wrote the firmware. It's embedded firmware. Your team wrote it, right? And you say, okay, I don't need to worry about it. I trust this firmware. But that firmware could be talking to the operating system or it could be talking to another agent external to that. There could be an error in this firmware, right? Somehow it gets exposed through a buffer overflow attack, something else like that. So all of a sudden, your expectation that this firmware agent was trusted and I don't need to worry about it, because the attackers were able to chain a sequence of attacks, got to your firmware, now all of a sudden, you're exposed. On the other hand, if you had built your IP block, the receiver had anticipated the situation that I do want to worry about the negative space. I will make sure that the packet sent by this firmware agent, I'm going to look for those malformed packets. I will look for those illegal opcodes. So even if this firmware agent got breached, I have defense in depth protection. So that is what negative space engineering is giving you, right? So if you are working you're a customer that's in a regulated environment. In fact, actually, it could be anybody, right? If you have data that needs to be secure and private, you need to be thinking about the underlying security of your entire stack, all the way down to the hardware. And having systems that are built with defense in depth gives you that additional peace of mind through the lifetime of the product, right? And so the vendor who demonstrates that is basically better capable of earning your trust.
Vivek, I want to just call out, you referred to hackers as bad actors. You and I are both representing N31, which is Intel's offensive security research teams, and I don't think they would call themselves bad actors. But
so we have the white hats and the black hats.
Yeah. It's all good. Finally, though, looking forward as we move into the era of AI, being all the talk these days, how does the negative space problem evolve, and how is Intel preparing for that future?
I think just like almost all aspects of society, right? I think everybody has to come to grips with exactly how does the advent of AI evolve in their respective fields, right? So in security, we often talk about security for AI and AI for security, right? And I think in our conversation today, I'll expand it to negative space for AI and AI for negative space, right? So the negative space for AI, if you think about the underlying technologies that are running our AI, right? The accelerators, the underlying data, the way we interact with AI through our prompts, right? One can think about the negative space in that domain. The protection of your data models. How do you protect against malicious prompts? And then you can then think about the bigger aspect of negative space of AI, the uses of AI, right? Deep fakes, or hackers and others, bad actors using AI to come up with attacks. That's a very big space, right? And it's an industry problem, it's a problem for society, and we have to come to grips with that. But let's not talk about that today. Let's talk about the other aspect of it, which is the use of AI for negative space engineering. And this is something that we are actively working on because this holds a lot of potential. Because AI is really good for looking for patterns, connecting the dots, right, which require a lot of human effort, right? So you can scale those out. That kind of labor-intensive or manual-intensive work can be scaled out to the use of AI. So for example, reviewing architectural documents for negative space. That's a classic use case that sounds amenable to the use of AI, right? You can enumerate the scenarios to look for, you provide the architecture specification, and AI can come out with at least the first cut on what scenarios to look for. So if you're in the blueprint phase of your architecture design, you get some blueprints or you get some mileposts on where to look next, right? So it's not perfect yet, it's improving, but it provides that initial data that can help make this can be more effective and can scale up. So there's a lot of potential there. And it really becomes a race again between people who are using AI for nefarious purposes and the protectors who are using AI to build these systems better. Right? So we are very actively working on that. I think negative space provides a very strong proof point or example for the use of AI.
Awesome. Well, Vivek, thank you for your insights on negative space testing. For those who want to find out more information, especially that quadrant diagram that you mentioned,
yes.
You can find that in our 2026 Intel Platform Security Report at www.intel.com/security report. And you can dig into some technical documentation from our Int31 team at intel.com/int31. Again, Vivek, thank you, and thanks for watching.